transmitter with, quote, load, which means could you dip the plate and get some kind of significant dip. And if you couldn't, and you looked at that frequency and you said, that's not where I want to be, so you went back up on the roof and back and forth and back and forth and back and forth. There's a guy that writes one of the articles I read where he says low SWR could kill you, and what he means is you can fall off your roof if you go up there often enough. But it's one of those things that we all know we're supposed to worry about. There's a series of articles that we'll get into in a minute that was published into a book by the ARRL in the early 90s called Reflections. And it was a summary of 7 articles written for QST by a guy named Maxwell, W. Maxwell. And he'd been an antenna designer for RCA and a bunch of different satellite type people. And in satellites, you know, you don't have any room and you got to put an antenna where you want it to be. And the transmitter's got to be where it wants to be. So you get pretty crafty at figuring out how do you load antennas with transmitters and so on with a transmitter in a confined space. He got frustrated in the early 70s and started writing these articles because there was so much boo-rah out there and old wives' tales. And if you know anything about a subject in ham radio or any other professional endeavor you have, and you go on a forum where people, and you don't know the credentials of the person that's writing his response, you're liable to see anything. And it's just the nature. So there's a lot of old tales out there about SWR. This is not a technical presentation. It's an understanding presentation. And so that's what we're going to try to do. Andre, one more. I think this has been created to keep hams out of the shack and on their roof. We all mess with antennas, or we're afraid to mess with antennas because of that nasty thing called SWR. Next. Okay, some common misconceptions. People think forward power is good, reflected power is always bad. Okay? Tuners just heat the shack. You'll hear people talking about that. All reflected power is lost. You're going to find out. No, it's not. I can't get out because of high SWR. Well, depends on why that is. If your cable's full of water, you might have an issue, but it's more than that. SWR 1.1 to 1 is necessary at all costs. And you'd be surprised how many arguments you hear of people bragging about their low SWR. I've done it. Build an antenna. Man, it's got low SWR. All right.
It's not resonant, Gil.
It may not be. We all know that with enough creativity, and we'll get into it over here, you can load a lawn chair. You can put 100 watts into a lawn chair. The pattern's probably going to be lousy. It may not be very good, etc. So there's a lot of stuff in antennas, but we're sticking here with power out. And some people think they always have to use a resonant antenna. I've given lots of talks on wire antennas, goofy antennas, antennas with 9 to 1, 4 to 1, 49 to 1 matching transformers, and people say, well, I really like to use resonant antennas. Well, we'll talk a little bit in a minute about what that may or may not mean. Okay? Okay, a little refresher on SWR, and we won't get much more technical than this. When there's a mismatch between the output impedance of a transmitter and the input impedance of the antenna, some of the signal in a form of a wave is reflected back down the transmission line to the transmitter. SWR is a function of input and matching impedances at the output of your transmitter. Okay? Standing waves of electrical energy will appear in the transmission line, and it's the ratio of the height of the standing wave versus the amplitude of the addition node. Let's go to the next picture. There may be okay, here's a little graphical representation. This blue line is the signal from the transceiver. This is the green line is the reflected signal from the antenna, and the standing wave, which is what SWR, standing wave ratio, is the vector sum of those two. Some places it's higher, some places it's 0, some places it's lower. It moves all over the place. All right. If the blue line and the green line are overlaid, so they're in phase with each other, SWR is 1 to 1. Okay, there's no standing wave. If it's not, you get something else. Go ahead. So the SWR, or most people talk, and we talk in terms of SWR, but it's usually the voltage standing wave, VSWR, is a relationship based on forward and reflected voltages. Forward voltage is generated by the transmitter. Voltage will be reflected back by a terminating load. That could be an antenna, could be a dummy load, could be an amplifier you're driving. The reflected voltage may or may not be in phase. We saw that. And if in phase, it would be 1-to-1. Okay. This is an excerpt from this old bird. He's passed now. But I have a feeling he was a real crank if he were at a convention talking to people. His papers, they're an interesting combination of easy to understand verbal written communication and a whole bunch of equations. You like fancy equations. All the hair is in there, but then he'll tell you what this really means. It's the only way I can understand. From the viewpoint of amateur communications, it can be shown mathematically and easily verified in practice that the difference in power transferred through any coaxial line with an SWR of 2-to-1 is imperceptible compared to having a perfectly matched 1-to-1, no matter what the length or attenuation of the line. So pure SWR doesn't give you a very big difference. Many typical coaxial feed lines that we use in the HF bands with an SWR of 3 or 4 and often as high as 5-to-1 have an equally imperceptible difference. And note, when feed line attenuations are low, the feed line is extremely important in getting power out through an antenna. In fact, that's the only place losses occur, no matter what the SWR is. Okay? And we'll get to in a minute matching issues with transmitters. Allowing such higher values of SWR permits operating over reasonably wide frequency excursions from the well-resonant, self-resonant frequency of the antenna with imperceptible power loss just described. And then he adds, he hates, in spite of the popular impression to the contrary. He was really fed up at the time he wrote these with the other stuff that was being written. Low SWR is relatively important when feed line attenuation is low. Again, we're talking feed line attenuation. And all power fed into the line minus the amount lost in line attenuation is absorbed in the load regardless of the mismatch at the antenna terminals. So you can have, and let's talk quickly, we'll mention some examples. We know people that are on the air with, they put out 500 feet of line for a long line. It isn't resonant on anything. They have to use a tuner with it, but it is at the antenna terminals, it's a hellacious mismatch, all right? I have vertical half waves, in-fed half waves, they're 3,000 ohm impedances. They're a terrible mismatch. We'll talk about how you can use them, but the antenna itself is a terrible mismatch. Still, you will get all the power you send to that antenna will end up at the antenna. Next. And then this is the two critical things. SWR is not the culprit in transmitter loading problems. The real culprit is the change in line input impedance resulting from the SWR. So if your transmitter wants 50 ohms and you're seeing 250, it ain't gonna like it. And it's gonna see that as an SWR mismatch. We have complete control over the impedance without necessarily being concerned with the SWR. And that's where he gets into tuners. And we'll talk about even old vacuum tube rigs had a tuner called the tank circuit between the tubes and the antenna. Next. And one last thing, it's the impedance of an antenna load seen by the transmitter that's the problem. If the transmitter output is looking for 50 ohms, it wants to see a 50 ohm load. If it sees 50 ohms, you got an SWR 1-to-1. You see 100 ohms, it's 2-to-1, and so on. If it sees 2,800 ohms, like my in-fed half wave, it'll be 56-to-1. Okay? Next. Okay. Let's talk about what is a resonant antenna. And does anybody in the room actually have a resonant antenna? I would suspect the only people here that have a resonant antenna are talking about a 2 meter or a 220 or a 440 antenna that's designed for a single repeater. And they've worked at it, so it is resonant, but at a single frequency.
How about 40-meter dipole?
Nope, it's not resonant.
Not resonant?
You'll see.
Okay.
It's resonant at a frequency.
Oh, yes.
A single frequency.
Yes.
You can't, and if you only want to talk to somebody on 7152, yes you do.
Yes.
If you want to go to 7160, not so much, okay?
Right. Yeah.
Hams usually define the frequency of a resonant antenna by the equation, and that's our old dipole friend, 469 over the half wavelength in feet for the frequency. And this length of dipole should have its lowest SWR, okay? But remember, dipoles, the impedance of a dipole is 73 ohms. 73 ohms, you can't get to 1.1 to 1 with a dipole anywhere, because it's going to be in the 1.4, 1.5 range, because you can't get there from here. It's got a characteristic impedance of 73 ohms. So we've all worked our whole ham career, if you've been an HF, and many of us started on 40 meters. Why? Because you got 66 feet in your yard somewhere. We've never had a quote, 1.1 to 1 SWR antenna, okay? Next, here's a plot. This is an EasyNet plot, but I got lots of plots on my own antennas. This is one where we got it's 30 feet. And anybody has done this, you go through and you plot your antenna, and what we always do is we say, all right, where are we going to operate? 80 meters is such a wide band that you kind of got to decide, are you going to operate phone and be in the 75 meter range, or are you going to operate CW and be in the lower end, or somewhere in the middle? This one is set at 3.6, and you notice it hits 2 to 1 at 355 to 366. Well, if you got a modern rig, doesn't like more than 2 to 1 SWR, and it's going to cut you back on power, you're stuck with 100 KCs to operate it. That's kind of confining. It might work for FT8 or PSK or RIDI, where you got these little windows. It worked great on that, but not for general operation. And if you've got an old tube transmitter that's happy with 3 to 1, you can tolerate 3 to 1. You might get, you get 3 points, whatever that is. So, what if you want to operate somewhere else? All right. When I was a kid, with my old tube transmitters, as long as I could get some kind of a dip, I didn't care. And I was only running 100 watts or 75 watts. If it got hot, it got hot. If you're running an amplifier, you got a much bigger issue. Okay, Andre. These are a resonant antenna beams. We all know you buy a tri-bander, it's resonant. And yeah, they do a good job of messing around with traps and so on. But you'll see that each of them, if you get high enough in frequency, most dipoles are good at 3%, 2.5%, 3% of the frequency. If you get up high enough, yeah, you can cover the whole band without a tuner. If you're down 40 meters, 80 meters, you have a tough time with that. Okay, next. So, in practical terms, what do we mean by resonant frequency? It's a range of frequencies where the SWR could be managed by whatever operating system we're using. If you've got an old tube-type transmitter, somewhere between around 3 to 1, you're okay. Solid state ones, you're 2 to 1. It's really the bandwidth over where your SWR is less than 2 to 1 for modern solid state transmitters. Why is that? Transistor finals operate at very low impedances, 1 or 2 ohms. You actually, in the output of those, use transformers as a matching device to get up to 50 ohms. In the old tube transmitter finals, they operate at very high impedances, 1 to 2,000 ohms, so you use matching networks to get down to 50 ohms. So these guys are a whole lot more sensitive. Also, slice open a transistor and see how close together things are, and you'll see why you don't want errant voltages floating around. Okay, next. Operating outside the 3 to 1 or 2 to 1 bandwidth of a resonant antenna. What do you do? Well, we've learned we have to use a tuner. Now let me back up a little. If you go back to the old boy that invented the G5RV, if you go back to some of the things you see with the Zeppelins, and there's a whole bunch of these old antennas, where you're actually using coax or twin lead feed lines as a matching network to match the antenna. Because we all know that a G5RV left on its own is resonant in 20 meters somewhere, somewhat. The rest of it you've got to work at. So, starting in the 80s, transceivers started to be offered with onboard tuners or accessory tuners sometimes, like my 930S has a built-in tuner, or you could get the outboard one. And they'll handle about 150 ohms impedance, so you're talking 3 to 1. The solid-state final transceivers all self-protect at levels greater than 2 to 1. If you wonder sometimes why you're not getting out, can't be heard, and we've had this on our RAGS net on Sunday night. Somebody's on the wrong antenna and they're transmitting at 2.5 watts instead of 100 watts because the transceiver is saying, hey, I'm protecting myself. Conventional outboard tuners can handle big ranges in SWR, sometimes very, very high, 10, 15, 20 to 1. And then there's all these new modern, and we got one up here, modern computer-aided outboard tuners, the ones that sound like a clickety-quack buzzsaw when they're tuning. They're really neat. They can go up to about 10 to 1. The digital tuner in my 450D will handle 10 or 12 to 1. So that's around. But the way we operate outside these bandwidths, if you're on 80 or 40 meters or 160, is you have to have a tuner of some kind, or you're limited in where you can operate, and you'll be back to up and down on the roof to make sure that little operating window is where you want to be all the time. But if you want to get out of that, you have to use a tuner of some kind. Okay? So let's talk a little bit about where's reflected power go. A lot of this came from mismatched antennas and plates and amplifiers turning bright orange when they're not supposed to be. And people say, aha, that's where the reflected power is going. No, that's a different issue. But basically, the reflected power travels up and down the feed line. It's in and out of phase with the forward power at some points. And except for transmission line losses, it all goes out the antenna. You're not losing it anywhere. It's there. And that's why you need to pay attention to low loss feed line. Okay, let's go to an antenna, everybody. People are familiar with doublets. We say put up a doublet antenna, which is a dipole, that is at least the half wavelength of the lowest frequency you want to operate. And you feed it with 450 or 600 ohm twin lead. If you talk to Randy out on the other side of the lake, I'm not sure how many watts he's running, but it's a lot. He runs 600 ohm feed line, okay? But what do we do with that 600 or 450 ohm feed line? It comes into a tuner. It comes into a tuner like one of these up here that has poles on the back so that you can actually run twin lead into it and tune it. Otherwise, it's not usable. The impedance of the antenna is 450, 600, or more ohms. All right? But all of the power, reflected power, all goes out. It's not lost anywhere unless you've got feed line problems. If you're using, and we'll mention in a minute, but there's low loss feed lines. There's high loss feed lines. I'm going to give you another example of a tuner that's part of the antenna. Any AM broadcast station, they're limited on tower height by where the nearest airport is, where other things are around it. And Gary, who is a broadcast engineer, he'll tell you that the base of all of these AM towers has a big ass loading system on the bottom, because they're using what they're allowed to use, but they got to load it to the frequency they're using. Another form of tuner. Go ahead, Andre. Feed line losses, ladder lines nil. Nil meaning a few tenths of a dB per 100 feet. RG58U, 2.5, sometimes 3, depends on the quality of it. RG8U, the bigger fat stuff's a little less than 1. RG8X is about 2. If you're going to run a feed line 200 feet out to your antenna, you need really good stuff. But remember, all of these are at HF. This is at 30 megahertz or down. If you go up to 144 or 440, the losses go right through the roof. And you got to use really good stuff if you're going to run a long distance on it. Andre? So, what kind of commonly used, very high impedance antennas are used with great success? But they use a tuner or a tuning network of some kind. We got doublets. Left on their own, they're a few thousand ohms in impedance. Folded dipoles are 200 ohms. In-fed half-wave wires, I've got several at home, 2,800 ohms. In-fed long wires, 2,000 to 3,000 ohms. You got to match them with something because a 50 ohm transmitter output doesn't like that. Okay, next. So, some examples of tuners and tuners in quotes. A tuner in quote will be vacuum tube final outputs have tank circuits. Any of us have started out with a vacuum tube amplifier. Know that you dip the plate, you increase, you dip the plate, you increase until you get to where you want to go. All right? If you look at the schematic, and we'll look at a couple in a minute, but you'll see the tank circuit is a tuner. Okay? Onboard transceiver tuners. There's standalone tuners that are quite traditional, and then there's these new LDG tuners that I think are just marvelous. If you're not running a lot of power. If you're running a lot of power, they got some marvelous ones out there, but they cost a little more. Okay. A typical pi network.
The way and barrel again.
Yeah. A typical pi network is you can, and those of you that, Ron, do this calculation while we're here, will you? You know, in your head, verify. But this is out of a text, but it shows a typical pi network. Why is it called a pi network? The capacitor, inductor, capacitor looks like the Greek letter pi. That's why it's called a pi network. But the load R will be transformed by the pi network to match some other value over here. That's what it's for. And if you want to go through all the calculations, you go right here. Okay, it's all good. It's all good stuff.
I'll pass.
I haven't done it. Go ahead. All right. This is a vacuum tube transmitter of some nature, and it's a multi-band one, so it's got networks, matching networks for each band, and that's what this switch. And inside this dash line, you'll see you got a variable capacitor, a bunch of inductors to match the plate output here to the plate tube circuit, which is several thousand ohms, to an output impedance of 500 ohms. Next. This is a little old 40-meter transmitter. Again, same kind of idea. Here's the tube. You're going through some kind of a matching network and out to the antenna. They're all there. Next. So, let's look at a few simple tuners. This isn't one of these up here. I didn't bring this one, but I have this one at home. This one belonged to Roger Hamilton, and who else owned it before you?
Bill Tully.
Bill Tully owned it, then you owned it, then Frank owned it.
And Frank owned it. Then Jerry owned it.
Then Frank and Jerry owned it. You can't kill these things. And if you look inside, they're pretty straightforward. But again, this one's got a vernier dial on it. But if you look inside, you got a big bread slicer capacitor. You got a roller inductor tuner. You got a series of capacitors around a switch here. This is a balun for the twin lead. They're all kind of about the same. Next. And this is the circuit for that. We won't get into it, but that's the circuit. Go ahead, next. This is a little travel tuner. I bought the other day at a ham fest an Elecraft K1. Runs 4 watts, 40 meters, 20 meters, has no tuner. It's the economical version. The guy that built it didn't put the tuner in it. And I was looking around and I found in a drawer this, and I can't even remember where I found it, but it's an MFJ Deluxe Travel Tuner with SWR, watt meter, and balun. It's good up to 150 watts. It's great. But again, you have you can handle a single line, you can handle twin lead, you can handle coaxial inputs, power to run the meter, light, and so on. And again, you got several bread slicer type capacitors and an adjustable inductor. Next. Then you get, I have 2 of these. This is the one that wasn't in a travel box somewhere. This is the one. If you decide you want to get one of these digital tuners, this is the one I would get, because this one is designed to go with my FT857. It's got a cable in the back that matches up with it. You have to use it with that rig, etc. The cable's loose, doesn't work. Plug in and plug out these cables long enough, and the little wires get bent. It's a pain. This thing, it comes on. You don't have to push a button. It senses RF and starts to tune. So you can actually use this in a weather-tight container out in the yard somewhere if you want to. It runs with 12 volts and senses RF. Looks like this. The circuit we won't look at it because it'll make your head hurt, because it's got computer chips and all kinds of stuff, and it's got all these banks. You notice all these inductors, capacitors, and relays. And when one of these things starts tuning for the first time and it doesn't know what it's looking for, it's pretty soon lights will start to come on, and there you are. And then it will remember that antenna. It'll remember what it saw the next time. So you change frequencies, come back, hit it, boom, it'll be right there. Okay, next. So a little quick summary. The SWR must be low enough to satisfy your rig alone or be tunable. What do I mean by tunable? I have some antennas I built where a good tuner, like one of these little ones or a big one, won't tune it. So you got to do something a little different. It means that the impedance of that antenna is so large that the tuner doesn't have the capacity to manage it. You need a tuner for minimum power loss and operating flexibility. You don't want to operate in a single band. My little K1 I just bought, it has 70 kilohertz, low end to 40, low end to 20. That's kind of, after a while, it's kind of, there's plenty of people to work there, but it's kind of confining. You know, you go up to the top and there you are, you're stopped, you know. So you don't want to be stuck with a narrow band. Reflected power is only lost in the feed line, and it's based on your coaxial characteristics. And you can find any coax you're using. Every vendor will tell you what their dB per 100 foot losses are. An open feed line has the lowest losses, always. Next. Good coax isn't far behind open line, but it is some. And even so-called resonant antennas have low SWR over very narrow bandwidth. You get out of that, it's not really low. Tuners give you great operator flexibility, and any required matching could be performed at the input to the feed line instead of at the load. Because once you've matched there, the feed line and the antenna is the load. So that's all, folks. If you got questions, discussions. Antennas are fun, as you may know. I think they are. I play with them all the time, and it's one of the things that any ham can build. It's like the project back there on the bench. Any ham can do that. And when you use an antenna that you built yourself, there's a certain amount of ownership, a certain amount of fun, and that sort of thing. Any questions? Either they went to sleep or they're sold. Thank you.